Alright, we're on number 4, 2018. The height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. Use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. Okay. So we're looking for 6, which is right there, halfway between 5 and 7. So we're looking for a rate of change. We're given the values. We'll just find... Okay, so basically, how fast... I'm going to interpret it first. It's how fast the tree is growing at 6 years, when it's 6 years old. How many meters per year the tree is growing at when the tree is 6 years old. So if after 5 years it was 6 meters tall, and at 7 years it's 11 meters tall, it's grown 5 meters in those 2 years, so I'm gonna say 2.5 meters a year. We just basically need to write that down now. So like let's formalize that a little bit. We'll take 11 minus 6 over 7 minus 5, because that's our average rate of change bit is 2.5. So at 6 years old, tree is growing 2.5 meters per year. And you want all of this because it specifically asks for interpreting the meaning using correct units. For part B, explain why there must be at least one time between 2 and 10 where the rate of change is equal to 2. For this, we're thinking like there must be an average rate of change that's equal to 2 because it's a twice differentiable function. Right, twice differentiable function. So we're thinking that there must be like a time where the average rate of change is equal to 2. It's clearly not between 2 and 10, which is our first try. That's 13.5 over 8, which is not 2. But between 3 and 5, this is 2 years. It grows 4 meters. So that's going to be our that's going to be our interval between 6 minus 2 over 5 minus 3 is 2, which is average rate of change. And then, since this is a twice differentiable function, since ht is differentiable, the mean value theorem says sum x between t between 3 and 5 has h of t equal to 2, h prime of t, sorry. C. Use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval 2 to 10. So it's kind of telling you what to do. Use a trapezoidal sum, yada yada yada. So average height, we're going to add up all the heights and divide by how many there are, approximately, right? So we're doing an integral, basically. Alright, divided by 8. So it's going to be the integral between 2 and 10 of h of t divided by 10 minus 2. Which is, okay, so our first one is between 2 and 3. That'll be 1. And then the average height, 1.5 plus 2 divided by 2. The second one, we go from 3 to 5, so that's 2 years. And the height goes from 2 to 6. The next one goes from 5 to 7. So that's 2 years. And the height goes from 6 to 11. The next one, it's from between 7 and 10, so that's 3 years. And the height goes from 11 to 15. And then whatever the heck that is. Yeah, whatever. 3.5 over 2. 8. 17. 3 halves of 26. 3 times 13, which is 39. And you can go as far as you want. D. The height of the tree in meters can also be modeled by the function g, given by g of x is 100x over 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter, x, is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? Okay, so we got some weird stuff going on here. We have a second, I guess, variable, x, which is not time, so we're going to have to do things a little differently. Let's write down what we know here. I don't know if this is all going to fit on this sheet of paper or not. So g of x is 100x over 1 plus x. And we know that when g of x equals 50, dx dt is 0.03. So I think, I don't know, there's a couple different ways to think about this. If this is straightforward enough, great. Check the answer key. I'm going to approach this a little different way, where we actually include the time variable. To do that, like, this just makes it a little easier for me to think about. I'm going to make a new function. The diameter at time t is x. So basically I can go through all of this and replace x with d of t. That's going to make it a little more obvious that we need the chain rule. That'll make things a little easier to understand. Actually, it might just make it easier to understand if we replace x with d for diameter. Then you won't be as tempted to think of x as time. Because what we're really looking for, right, we're looking for the rate of change of height. Like, looking for g of the derivative with respect to time of g of x, or the derivative with respect to time of g of d of t, of, that should not be an equals there, of g of d of t. So if we do that, okay, so this will be g of d of t is 100 d of t over 1 plus d of t. Now, you know, actually, that's really not g of d of t. That's just d of t. It might be an easier way to think about it. So we'll take the derivative, right? Derivative with respect to time of both of these. So this will be g prime of t. And this is what we're looking for when the height is 50 meters. Now, t is not x. But, yeah. This derivative, we will need the product, not the product rule, the quotient rule, and eventually the chain rule. All right, so derivative of the top times the bottom. Okay, so this is 100 d prime of t times the derivative of t, but this is just equal to 1. All right, because this is the derivative of t with respect to t, which is 1. Times 1 plus d of t minus the derivative of the denominator, which is 0 plus d prime of t times t prime, but, you know, times the top, all over 1 plus d of t squared. So this way we do need the chain rule, but it's just for t, and we can kind of ignore it. So now the question kind of is, we know what d prime of t is. What we don't know is what that is a prime written there. It's just not very visible. What we don't know is the diameter when the height is 50. Given that x is the diameter, we'll just write that in. Okay, so this is the height. The height is 50, and this is 100 d of t times 1 plus d of t. Multiply by 1 plus d of t, we have 50 plus 50 d of t equals 100 d of t. Subtract 50 equals 50 d of t. So when the height is 50, the diameter is 1. Now, we know 0.03, we know 1, plug them all in, we have 100, so g prime of t will be, all right, 100 times 0.03 times 1 plus d of t, 2, 1 plus 1, minus 0.03 times 100, all over 1 plus 1 squared. Whatever that is, 0.03, 2 times 0.03, or it was 2 times 3 actually. 100 times 0.03 will be 3. 2 times 3 minus 3 over 4 is 6 minus 3 is 3/4. I don't think this asks anything about interpretation, so we are just fine with 3/4.